So good evening, as the title suggests, I will be talking about spin cones, which is a form of arrangement of spins in random field X5 models. So this is a work which Musansi started with a project student, Ananya Janardhanan, which when she left, I carried forward. So the plan of the talk is as follows. I'll first describe the model, then describe zero temperature spin distributions in small disorder regime, then go to large disorder regime, and also talk about certain metastable states. And finally, I will allude to time scales associated to formation and orientation of cone, more of which will be clear as I go forward. So the model is described using this figure here. So consider n sides. So an example with 4 sides is given here, in which all sides are connected to, every side is connected to every other side. So at each side, there is a spin, Si, which is of modulus 1 and can have any direction in 2-dimensional X space. So every spin is a fully connected graph. Every spin interacts with every other spins with equal cost of energy. And at each side, there is also a random magnetic field, Hi, which has the same magnitude but a different direction in the 2D space. So the direction is denoted by the unit vector Mi, which is drawn from a probability distribution such that it lies equally, like it is equally likely to lie anywhere on a unit circle. So the Hamiltonian which describes the system is given by this, where you have this term where spin couples with each other and this term where spin couples with the random magnetic field. So spin models with random fields have been studied in a variety of contexts. It was first introduced by Larkin in the context of superconductors. Our focus on X5 spin models with infinite range interaction, which has applications in neural networks and so on. So the phase diagram in general depends upon the distribution from which these random fields are drawn. So for a uniform, for a distribution which is uniform over a circle, you have the following phase diagram in the temperature and the modulus of the random field plane. So this is a locus of second order phase transition, which is separated by a tricritical point by a locus of first order phase, from a locus of first order phase transitions. This is the ordered state and this is the disordered states. What we will be interested in how the spins are distributed in the ordered state here in this regime, which one can follow using very simple calculations. So this is directly the result that we are talking about. So in the limit h by j tending to 0, all spins point along the direction of vector sum of fields. So if you notice, this is actually can be thought of as spherically symmetric, not spherical, 2-dimensional rotational symmetry abiding system, because you have the classical spins. And these MAs are random fields which are drawn, which can easily probably lie anywhere on a unit circle. But for any finite n, rotational symmetry will be broken, and there will be some direction which is chosen. So that is given by the direction of vector sum of all the fields. So this is the direction in which the spins all point in the limit where the disorder strength tends to 0. So for small h by j, all spins fall within a cone. This is what by definition we call a cone. It's a 2-dimensional object anyway. So, and the distribution within the cone is as depicted here, which diverges towards the edges of the cone and is minimum towards the center. So the center is not exactly the direction of vector sum of fields, but there is a small tilt from the direction of vector sum of fields due to the strength. So we can quantify the phase transition using the cone angle. When h by j increases, the cone angle increases, and when it is about 90 degrees, there is a first order phase transition. So it's in summary, so these results can be obtained using very simple techniques. For example, at 0 temperature, you can write down the Hamiltonian, and in terms of the angles that the spin and the fields make. Then you can extremize with respect to the angles theta I and solve this equation perturbatively to obtain the distribution. So this is how we proceed. We solve perturbatively to obtain an answer for each spin theta I in terms of the field angles. So here alpha naught is the angle of vector sum of fields, so which is given by this, and eta is a parameter which is decided by the arrangement, the particular arrangement of fields. So one can also deduce an orientation of the total magnetization from this, which is given by theta naught. Now, if P tilde denotes the probability distribution from which the angles alpha i's are the angles of the fields are drawn, which is equally likely to lie anywhere on a unit circle, so it's 1/2 pi, then we can find the probability distribution for delta theta I from the solution for described. So this is the solution. This is the distribution for delta theta I, which explains how the spins are distributed, which is diverging towards the edges and minimum towards the center of the cone. So all these features that has been pointed out in the beginning can be explained in terms of this. So finally, you have a cone angle which widens to as 2 times h over j. Now this is in the perturbative regime. So we can go to non-perturbative regime in h by j using the technique called numerical continuation. So these are a result for a particular realization of fields of say 200 spins. So the second diagram shows the ordered phase distribution of spins. So the distribution can be is seen in this figure F. So h by j is 0.2. You have a distribution as predicted by the perturbation theory here. Then about the phase transition, which varies from sample to sample. For this particular sampler, the transition occurs at just above h by j 0.62. You have the cone angle about 90 degrees. So that also fluctuates from sample to sample, but on an average, it is about 90 degrees. Then when slightly larger h by j, you have the disordered phase in which the spins are pointing all around the circle. And here if you plot the magnetization, you can clearly see a first order jump at the point of transition here. And this figure shows how the cone angle widens and the cone stops existing at this point. So if you plot the energy of the minimum states, you find it, you get this figure. But you also find that there are certain metastable states or local minimas near to the phase transition. So the blue dots are dots in which the spins are arranged within the cone, and the circles denote as disordered systems. So there are disordered phase in this regime, and there are ordered states in this regime, but they are of higher energy than the. So I will skip a few and finally quickly go to the time evolution of spins. So the time evolution is characterized by two time scales. The first time scale is the time scale in which a cone is formed somewhere around the circle. So then from A, spins go from A to B, and in a larger time scale, the cone orients towards the equilibrium direction. So there are a lot of interesting features regarding that, which I won't go through. So in summary, what we have looked at arrangement of spins in the ordered phase. And we have pointed out that the phase transition occurs when the cone angle is roughly 90 degrees. So we looked at existence of metastable states. We skipped over the rest and also looked at cone formation and orientation times. So one can also look at crystal fields where you have a coupling which is squared, mathematically very similar, but physically describes very different system, which are amorphous magnets. We also have cones at this one. The distribution of spins is identical within the cone. The orientation is different, and there is no phase transition at 0 temperature for this model. So further details is given in this archive. Thank you.
Questions?
The MIs were random fields, right?
small mi is where random.
Yeah, random unit vectors.
But then what sets the direction of the cone? I mean, that let's say when h is very small.
So the direction of the cone is
determined.
No, it is determined by, for a particular realization, it is determined by the set of MIs.
Okay. It depends on the particular.
Any more questions?
Can you go back to your original Hamiltonian in the second slide or something? Yeah, okay, so then effectively, so you're but you said you're having the spins always with the same magnitude, the magnetic field, sorry. But it just changes direction.
Yeah, at every
but
site.
Effectively, you're changing h. So
effectively,
I mean, you're changing h as a ratio of h by j, right?
Yeah.
So I mean, in that sense, the field is not really of the same magnitude all the time, is it? I'm a bit confused about this.
Oh, okay. We are changing h as a parameter. And
no, you have different values of h by j.
So, yeah, for a particular realization, you have same h, you have different directions at different sites. So, if you want to think of it that way, then we study how distribution changes with different h.
But aren't you, I mean, just drawing these from some kind of a, okay, only the thetas are drawn from a distribution.
Yeah, only thetas are drawn from the distribution. Okay. The strength is in our hand.
Okay, we can talk.
Yeah. Any other question? Okay, so let us thank the speaker once more.